Okay, now we're going to look at the formula we get for the angles theta, where we get the bright bits of constructive interference from a diffraction grating. So I'm going to imagine that this is just a real zoom in of my diffraction grating. I'm just going to be looking at two nearby sort of holes in the diffraction grating, and I'm going to call the difference between these d, little d. Okay, and we know that if the light going through at an angle of theta along this path and along this path ends up in phase over here, then the path difference must be a whole number of wavelengths, and of course we're going to use lambda for the wavelength. Okay, so from this point onwards, that's where they have to be in phase. So the path difference I get by drawing a right-angled line down from here, okay, and this difference here, that gap there, has to be a whole number of lambdas. So it would be a whole number n times lambda. Okay, so now I'm doing quite well because I've got a right-angled triangle. Okay, let's draw it, go over it in blue. This right-angled triangle here. Okay, I've got a d there, I've got an n theta here, and I've got an angle theta. Now this theta, the angle that the light's coming at, okay, is the same as that angle theta. How can I convince you of that? Well, I think I can say that the straight-on direction is here. The angle between the light, there it goes, and theta is this angle here, this is theta here. So this angle here, which I haven't got room to label, but I'll do it down here, is 90 degrees minus theta. Okay, not minus lambda, that's rubbish, minus theta. Okay, and since I've already got a 90-degree angle in my right-angled triangle, these other two must add up to 90 degrees, so that justifies my claim that that one must be theta again. Okay, so that was just to justify that claim. So I've got n theta there. This distance here is my n theta. This distance here is d. Okay, and I'm just going to use SOCAR TOA. Okay, so SOCAR TOA tells me that sine of theta, okay, equals the opposite. Now in this triangle, the opposite is well, let's do opposite over hypotenuse. That's what SOCAR TOA tells me, and then let's put the values in. So the opposite is this one here, which is my n lambda, and the hypotenuse is this one here, which is d. Okay, and that's sine theta. So if I multiply both sides of that by d, I get that d sine theta equals n times the wavelength lambda. Now n can take different values. Remember that n just came from saying this is some whole number of wavelengths here. So it will happen when n is 1, and when n is 2, and when n is 3, and so on. And as you increase n, you'll increase the value of sine theta. So you'll get various different fringes. The fringe when n is 0, when n is 0 and there's no phase difference, no difference between the path lengths, sine theta will be 0, and the light's going straight ahead. Okay, and the spot you'll get there is the one that's in the direct centre, hitting the spot that the laser would hit if you just left it to its own devices with no diffraction grating. And then the other spots will appear at different angles theta, and the first spot to appear will be when n is 1, and that will be called the first order fringe, okay, and that will be for the smallest non-zero value of sine theta will be when n equals 1, okay, and then when n is 2, sine theta will have to be a bit larger, and you'll get another fringe on either side for n equals 2. Okay, and when we do this, we tend to work, as I say, with this angle theta where the fringe appears, rather than the distance away on a flat screen. And quite often you see diagrams when people talk about this, where the projection is actually onto a circular screen, because that maybe makes it a little bit easier to just visualise chopping the arc up into these angles. Okay, but anyhow, we've reached this formula, which is in your data booklet, and is one that you're expected to apply.